Are we all set to start? Am I audible?
Yes.
Okay, let's wait for another 2 minutes.
Okay.
I can see some people joining. Yash,
Yes, ma'am.
can you please post on your group that let them connect with audio so that they'll be able to speak and interact?
I'll send the post.
Yeah, because what is happening is students are not connecting with audio. Perhaps they have forgotten to click on connect with audio, computer audio.
Yes, yes.
Yeah, please do that. Thank you.
Yes, ma'am. Yes, ma'am. I have posted it on the group.
Posted it on the group? Okay.
Yes, ma'am.
Fine. Should we get started now? It's 3:05. Because then again after 40 minutes, we'll have to, restart it. So should we get started? Let the students keep on
Yes.
joining. No worries.
Okay.
Okay, let's get started, class. Now what I'll be doing is I'll stop my video so that we have. Okay. Yes, everybody. I hope all of you are doing very good and taking good care of yourselves. Yes, everyone.
Yes.
Okay. What I'll be doing next is I'll mute all of you and we'll start with the session. And I'm sure all of you are aware that there is an option where you can raise your hand and you can please feel free to stop me at any given time. Is that okay? So that we can avoid crosstalk and chaos. Is that okay, class?
Yes.
Okay. Here I go. I mute all of you. Please raise your hand. I'm sure all of you know the option there. You can raise your hand and pose a question any given time. So here I go. Okay. Fine. Let's get started, class. Today, in this session, we'll get started with the most important bit as far as it goes to machine learning and artificial neural networks. And the bit that we will see today is backpropagation algorithm. So I'll directly take you, I'll share my screen and we can get started with the algorithm. Let me know once you see the screen. Here we go. All of you. Is that okay, class? Are you all able to see it?
Yes.
Okay, good. Let's get started. Now, during your practicals and even during your theory lectures, you have already studied the fundamental learning rules. And the rules that you have seen are like Hebb's network, McPett's network, and perceptrons network. Now, while you have studied all these rules, the fundamental zest of human learning, which is improving ourselves, is somewhere missing. That is the first important thing which all of you must have come across. Second most important thing is we kept on changing the weights. We kept on either adding them or subtracting them. But everything that we did, it was trial and error base. We never had a very sophisticated or a proper algorithm to do it. So if you remember MacPits, you randomly started with some weights and then you kept on looking at the values that you get, and uh, does it give you minimum error? So all these algorithms you were doing it randomly. When it came to perceptron learning algorithm, you did have a formula to update the weights. But the zest of backpropagation algorithm, if you take a peaceful look, is you can always have a look at the screen. As you very clearly see, there are three most important stages to backpropagation algorithm. The first one is the forward pass that you can take a look at. Forward pass, which starts right from your inputs. These are the inputs that you have. You may have as many as hidden layers that you choose to, and we have taken a simplest case where you have just one output. So the first path that you see here is the forward path, forward propagation, the path that you see. So the first path includes, given the inputs, randomly we give the weights and we will go for the forward pass and we will find out what the output is. Moment you get the output here, we all know that backpropagation is a supervised learning algorithm. So considering a training set, I know what is the actually expected output. And then what is the output given by this net? Using both the values, I calculate the error. So this error is being calculated. Once the error is calculated, I update the weights accordingly in the backward propagation. So this error is propagated backwards. Now, what are we actually doing when I say that the error is being propagated backward is, please understand that we randomly assign some weights here. And the learning algorithm is a gameplay of changing the weights. You just cannot do anything about the input. Input is given to you. Output is also given to you. So any learning algorithm, if you take a look at, if you try to recollect, uh, it is nothing but adjusting the weights which are assigned in these layers. Now, what are we doing in backpropagation is, we are changing the weights in accordance with the error. The best example which I end up giving is, let us say I am a wholesaler in some business and there are three people who contribute to my business. Let's say it's a fruit business and I take 100 fruits from a retailer 1 and then 10 from the another person B and another 10 from the third person C. Now if I have some profit, I cannot end up distributing it equally. The person who has contributed the most should end up getting the most maximum share of my profit. On the other hand, if there is a loss that I have, I cannot divide the loss equally amongst the contributors who have given me 100 fruits, 10 fruits and 10 fruits. It should go as per the contribution that they have. So this is exactly the principle which is being used in back propagation algorithm. So if you see the back propagation part here, red arrow, third number step, I will calculate the error, and this error will get multiplied by the weight which is being assigned at this particular layer, and accordingly I will change the weight. So we will very clearly see what these steps are and how gradually it will bring us down to the final value. Now, all of you, I'm sure that we are all aware with the activation function concept. The thing that you have to remember is during forward pass, I use activation function, which you have not used in earlier learning rules. Earlier learning rules, all you have taken is a weighted sum. Given an input, you did multiplied by the weights. There was some input given here. You multiplied it by the weights and you found out how much the output is. In back propagation, for the very first time, you are going to use activation function. You have already performed a practical on it. So I will not go in depth for activation function. So let us get started with the steps. As of now, I stop sharing my screen and I would like an acknowledgement from all of you if the basic difference in back propagation is clear. Why am I calling it as back propagation? I'm propagating the error back. Where am I propagating it back? To these hidden layers. What is the objective of propagating it back? So that I change the weights. Why is it necessary to change the weights? So that I achieve the best fitting line. And what do I achieve by propagating the error back? So that the change in weight is according to the error that I have got. So here at this particular time, I stop sharing my screen and I come back. I come to all of you. And yes, everyone, I unmute all of you. Can you all please tell that is the first step very clearly understood? Yes, class.
Yes, ma'am.
All of you. Do I have to ask if all of you are occupying the first bench on the in your rooms?
Ma'am, last bench.
Last bench. Okay. Good enough. Okay. So fundamentally, the first difference is clear, everyone? Yes or no, class? Come on.
Yes, ma'am.
Okay.
Yes, ma'am.
Okay. Now I'll directly take you to a solved example. Yes, class. Yes, dear.
Yes, ma'am.
Okay. So now what is it that I do next is, let's directly go to a solved example and let us very clearly see that what are these steps, what is it that I'm doing, and how is it that finally I end up achieving the algorithm, or what is the learning rule. So I start here again. I come back to sharing my screen and we get started here. Here we start. All of you, can you all see the screen?
No.
No, ma'am.
Okay. Okay. Can you see it, dear?
No, ma'am.
No? Give it a while.
It's starting.
It's starting. Give it a while. Let's give it a while.
Yes,
ma'am.
Okay. Yeah.
Yes.
Okay, let's start now. You see a fully connected network here. Why am I calling it as a fully connected network? Please remember, class, there are various architectures that I use in neural networks. What do I mean by architectures? Various styles of connecting the neurons. Now, this is my input layer. This is the hidden layer that I have. Okay, I'll use the mouse so that you all understand. Give me a minute. Okay, here. Okay, so if you see, okay, the one that is marked with X, the thing that is marked, all the neurons that are marked with X are nothing but your input layer. This is nothing but the input layer that you have. The ones with W is nothing but, ones with Z is nothing but your hidden layer. And the output layer is nothing but Y. Now this particular example is a solved example from our standard reference book named as Shivanandan. I'm sure you must have used it. What are we going to do is let us understand it and let us understand the passes which are involved. I call this as a fully connected network. Why do I call it as a fully connected network? Because every neuron on the input side is connected to the next neuron. So you see that there are 3 layers given, and each neuron in the previous layer. So if like now, if you can see me using the mouse, this is the input layer. Every neuron here is connected to the next layer in the next neuron in the hidden layer. So every neuron in the hidden layer here is connected to the output neuron. So I call such a network as a fully connected network. The weights are V. In the hidden layer, the weights are W. And these are the final outputs, Y1, YK, and YM. T1, TK, and TM are the targets value. I repeat once again, it's a supervised learning algorithm. We always train the network on the training data set where I know what the output is. Let us get randomly, I start randomly with some weights and let us see how do we go ahead. So let's start here. Okay. Before that, let me go back and note it. Okay. Yeah. Let's get familiarized to some terms, everyone. X is nothing but the input training vector. T is nothing but, I don't know, just give me a minute. I'm sorry, just give me a minute. Okay. Going back to, give me a minute. I'm sorry for this class. I go back to sharing my screen. Okay. Is it okay, class? Yeah. Here we start. Now, all these notes, they must have already reached you, or else I'll post it on the Google Classroom once again. I want you to please pay attention to the terms that are now involved. X is nothing but the input training vector. So let us say I have 3 bits in my training vector. So these are the 3 neurons which correspond to the input training vector. T is nothing but the target output value. Like you must have seen in AND gate, when the input is 1 and 1, the target value is 1. So this is basically your target value. Alpha, one new term which you must be coming across. This alpha is nothing but, alpha is called as a learning rate, the rate at which I learn. So this alpha, if it is very high, I will reach my target very soon, but learning will not be effective. If my alpha is very small, I will take a lot of time to reach my target. So to give you an example of this, let us say we have to complete machine learning entire course in 5 lectures. So my learning rate will be very high. So for let us say 6 lectures. So every lecture I complete 1 unit, let's say. So we will be doing it for the sake of doing, and the learning will not be very Good, because the learning rate is very high. On the contrary, same machine learning course, let us say I am given 60 lectures. Now I can have 10 lectures for each class, for each unit, and the learning that happens will be better. Please remember, learning rate should not be very less, because then the time that I take to learn will be very high. Neither should the learning rate be very high, because if the learning rate is very high, I will reach my target. In fact, there is a chance I don't reach my target at all. So please remember, we should strike a balance between these values of alpha. 0 and 1 are the minimum and the maximum values that are taken. So anyways, you'll understand it better as we see the example. Now let's start. Xi is nothing but your input. Zj, it is the hidden layer if you see here, Z1 to Zp, Zj layers. Yk is nothing but the output unit. And then coming to the most important factor in backpropagation, which is your delta k. Delta k is nothing but your error correction written as EC, weight adjustment in the output layer, that is adjustment of weights from output to hidden, that is W. So if you see here, it is W. Similarly, delta J is the error correction or the weight adjustment as we move from hidden layer to the input layer. So let us say if I have 10 hidden layers, I'll be having this for each and every layer. I hope these terms are very clear, because we will be using them in the numerical as well. Let me directly take you to the forward pass and then to the backward pass. So let me take an example so that you understand it better. And after we look at the example, I'll take you to the generalized representation of it. So this is the example number 9 on page number 91 of the soft computing book. And let us understand what the forward pass is. So the forward pass is something very similar to what you have been doing earlier in the earlier learning algorithms. I take weighted sum, but as I did mention, the most important part here is application of the activation function. You have already performed the experiment on the same. So let us get started. Now Z1. Z1 is nothing but I'll have weighted sums of all these 3 neurons. So what is it that I have? I'll have 0.3 into 1, 0.6 into 0, and this is minus 0.1 into 1. So please see this Z in 1 is the input given to the first neuron. Input to the first neuron. So what will the input be? Weighted sum 0.3 into 1, 0.6 into 0, and minus 0.1 into 1. This is 0.2. This 0.2 will now be applied to an activation function. So what is Z in 1? Sorry, Z in 1 is the input, and Z1 here, if you see, please focus on the mouse. Z1 that I have is a function of Z in, and this function is a sigmoid function. So I have this sigmoid function is 1 upon 1 plus e raised to minus x. So 1 upon 1 plus e raised to minus 2, which is nothing but 0.54. Similarly for Z2, I will have, can we do it together class? 0.5 into 1, minus 0.3 into 0, and 0.4 into 1, which brings me down to 0.9. Similarly, as we did it for Z1, Z2 will be a function of Z in 2. So what is the function? What do I mean here? Z in 2 is this, the weighted sum. I am applying a sigmoid function, which is nothing but my activation function in this case. So the answer that I get is 0.7. Same step will be repeated for the final layer. So if I take a look, let me minimize it slightly so that we are able to see the diagram as well. I think it's too small. Similarly, for the output layer now, this is 0.4. My Z1 is 0.5. Z2 is 0.7. I'm only reading it to the first place, and plus this bias factor. Similarly, if you see y in will be 1 into 0.2. Okay, 0.5498 into 0.4 plus 0.1 into 0.7109. So it is again the weighted sum. Again for y in, I will apply the activation function and I will reach the final answer. So the forward pass that you have just now seen, it is a very easy thing which you have already done. Now if I can generalize it for you, does this diagram make it any simpler for your class? I have x0, x1, x2. These are the weights that I have. So do you see that the hidden layer, I am actually splitting it as Z in 1 and Z1. So do you now map it to what we wrote in solving the example, where I wrote Z1 function of Z in, Z2 function of Z in 2. So what is Z in 1? Weighted sum. What is Z1? Function of Z in. What is Y in? Weighted sum input. Y in input to Y is nothing but weighted sum W into Z1, W2 into Z2 plus W0 into bias. This is the weighted sum. What is Y? Y is nothing but function of Y in. Which function? In our case, we are taking sigmoid. So does this table now make sense? X, I have 3 inputs, x0, x1 and x2. This is nothing but the weights. So what will I have? Z in 1, weighted sum, x into v. Z in will be x into v. What will Z1 be? Function of Z in. So 1 upon 1 plus e raised to minus x. This case. Similarly, y in weighted sum, xi into wi. What will y be? Again, sigmoid function. So at this particular point, I again stop sharing my screen and I would like to talk to all of you that is the forward pass clear? Here I go,
Yes.
unmute. Yes, class.
Yes.
Yes, yes.
Okay.
Ma'am.
Okay. So the
Yes, ma'am.
forward pass is pretty clear, everyone. Very good. Let
Yes,
us
ma'am.
okay, class. Okay, good. Thank
Yes.
you. Okay. So let us now go.
Yes, ma'am.
Can you please raise your hand? Someone who has a doubt?
Raise your hand. How?
Okay, here I have someone.
Oh my God.
Okay. Okay. Yes, Suesha, please tell. Yes, Suesha. You had a doubt? Yes, Jayesh also. Yes, Jayesh, please speak. Okay, it looks all of you have lowered your hands. I assume it is all okay. We are good to go to the next step. And I'll put all of you on mute so that my voice is clear. Let's again go to the most important step, and the step is back propagation. Here we go. Okay. Okay, let's start. Now, going to the next step, this part is clear. I'll bring you back to this step. Let us understand what is it that we are doing. Now, most important concept here, which usually is called as a gradient descent algorithm. I want all of you to understand the concept of gradient descent. What is it that we are actually doing, and why are we calling this algorithm as gradient descent algorithm? Let's have a quick discussion on the same. What is it that we ultimately want, class? Ultimately, we want the error to be minimum. Now, when I say that the error has to be minimum, any function for that matter, when you want that function to minimize, what is it that you do? You end up taking a derivative of it and you minimize it to 0. So gradient is nothing but I take the derivative of the function and I try to minimize it to 0. This is what I actually do when I say that it is a gradient descent algorithm. Now, if you take a look at our back propagation phase, the most important thing that happens is, okay, I don't know why do I have, okay, here. So here, if you now focus on the screen, our objective is looking at the back propagation phase. If I now have to see the output that I have got in the first phase is 0.5227. Given target was 1. I'm sure you can all see it. I'm trying to get rid of these arrows. Just give me a second. Here we go. Okay. So here we have it. Please focus on the mouse and ignore the arrows that are there on the screen. Now the output that you have got in the forward phase, it was 0.5227. If I quickly take you back here again, first phase, we calculated Z1, again weighted sum, we calculated the final net output, which is nothing but Y. So the Y that we got was 0.5227. Now this is the output that I have got with the given phases. This output is 0.5227, jabki the output, the given target, if you see this PDF, the given target is 1. I am increasing it. Okay, so the given target value is 1. The first thing that I do is I know that the output I have got is 0.5 and the given target is 1. So I know that I have not achieved my target. Now, if I have not achieved my target, that means there is an error. This error could be positive, could be negative, in any ways. Whenever we are having this error, the only thing that we end up doing is we uh, have to update the weights, and that is where our last phase of updating the weights comes in picture, which is also called as back propagation. So what is it that I do for back propagation? Let's quickly revise what we did for the during the forward pass. I took the weighted sum and I applied a sigmoid function on it. Now in the backward pass, when my objective is to reduce the error, I take the derivative and I try to minimize it to 0. So if you take a look at the delta k, what was delta k? Delta k is nothing but the error correction. How much is the error? Tk, that is the target value, minus yk. What is yk? Yk is the output that I have got in the first during the forward pass. So the error is tk minus yk. And please focus your attention on f dash of y in. Please understand what we are doing here. This particular point of multiplying the error by derivative, which is nothing but gradient, descent, decreasing gradient. So if you check the derivative of a sigmoid function is f of x into 1 minus f of x. So I'll again share it with all of you. This is the screen that I had. Hold on. I wanted to share you. Yeah.